So, welcome back everyone, and in this video we're going to start talking about recurrent neural networks, which is a different neural network architecture than we learned so far. So far we learned the forward neural network, or fully dense, fully connected network, multi-layer perception, whatever, like these are like rather synonyms. And recurrent neural networks and convolutional neural networks are two other architectures which are substantially different from the forward neural networks, but are also very popular and are very frequently used. Okay, recurrent neural networks is something which processes information over sequences, typically over time. Okay, so this is like what's new here. Convolutions is something which you may consider to be some sort of filtering process, but just as where we're going to take a look in another video, or in a few videos we talk about convolutions. Okay, but when it comes to recurrent neural networks, I think the most important attribute you need to consider is that you use typically recurrent neural networks when you have like sequences of something. Okay, so we typically in the financial area, it's kind of easy because typically sequences over time are very common and important to us. For instance, consider stock prices. Okay, we usually may be interested in the process of the stock price, and so we have a sequence of the stock price. For instance, the last 5 days, so the 5 working days where the stock price is traded at an exchange. This is maybe a sequence, and even though it will not be that easy in reality, but for the moment you can picture, for instance, we use the information of the past 5 trading days in order to, for instance, try to predict tomorrow's stock price. Disclaimer here, this is usually not going to work and it's not that easy, but for the moment let's let's try to pretend as it is possible. Okay, so when we have a recurrent neural network, our data typically would look like we always have 5 days, for instance, or it could be 3 days, or it could be 10 days. A few days, we have the information of the past stock prices, and we may be interested in the next day's stock price. And so the recurrent neural network is supposed to, shift the information over time, or go through the information over time. So it will process through the 5 days, for instance, and try to identify maybe patterns. So assume there is some kind of a sinusoidal curve relationship, so something like this. So a recurrent neural network may process through 5 days of prices, of price information, and try to learn something here. Okay, so this is like the characteristic that is necessary in order to successfully apply a recurrent neural network. Okay, but before we go too much into detail here, let's take a look how recurrent networks are often formally described. Okay, so we again have some sort of what is called the hidden state, or like the neuron, the recurrent neuron here. You may often or sometimes see something like this here, what I personally do not think is quite helpful. But it's like describes a recurrent network as, given some information X. So the information at some point in time is then processed to a hidden state, and something is done here, something is calculated, whatever. And this information again is fed back into the next step of time. Okay, but if you unfold it, I think it's quite easy, or more easy to understand what's happening here, because below here we have the information which is processed over time. In our example, X is a univariate variable, so it is just a single stock price information at a given point in time. But it could be more variables at each time step. For instance, at each day we could be interested in using the information of the stock price itself, the volume maybe, or I don't know, the highest price at the day and the lowest price at the day. So we would have 4 feature variables, and for each feature variable we would have information at a specific point in time. Okay, but for the moment, let's treat it in the most easiest way. So assume that this is only a single information or a single feature variable, but it's the information is provided at each step in time. Okay, so we would I don't know, the stock price at day 1, the stock price at day 2, at day 3, and then the stock price at day 5 here at the end. Then what we have is in the recurrent network, or basically this is not the network, this is like how a recurrent unit or a recurrent neuron is constructed. So it starts with a hidden state. Usually this, you could picture this as a value which is initialized with 0 in the beginning. So in the beginning this is a 0, and then we have some mathematical calculation that adds the information of the previous hidden state. So in the beginning it would be 0, and then it combines the information of the previous hidden state with the current information at time step t. So in the beginning, the first time step, so we would have the hidden state in the beginning, which is 0, and then we combine the information with the current time step t, so at the beginning it's time step 1, in order to somehow calculate the hidden state at time step 1. And then this is done again and again. So the hidden state at time step 1 is combined here with the information at time step 2, which is provided by the feature variable, in order to calculate the hidden state at time step 2. And this is done again and again and again. So the recurrent unit or the current neuron basically goes through the information which is provided by the feature variable, but hereby accepts the time structure. So it also implicitly accepts the temporal difference, the temporal dependencies which may occur here. And it goes like a train. It goes through time and always collects the current information and combines the current information with something that is calculated on the basis of the past information, which is here the hidden state. And then we end up at a certain point in time. Okay, so this is like, I know in the beginning this is hard to picture, and we will take a look at a very simplified and easy example which I will write down by hand, but first let's just finish the explanation here. Okay, so this of course this can be done not for only a single time, this can be done for many times. So we can generate a vector of hidden neurons. The only difference, as you know it for forward neural networks, is that we will use different weightings here in order to generate different values of hidden states, which will generate different neurons. And as I said before, also we can use at every time step, we can use more than one feature variable. So we can use a multitude of feature variables which processes information, or which through which information enters at each time step. Okay, and again, how exactly do we calculate the hidden state? This is kind of similar as before. So as the input, as you can see, we have the hidden state of the previous one. So basically this is a 0 here. Please, I'm sorry for that. Oh no, sorry, no, that's the one. That's sorry. Everything's all right here. So if of the previous hidden state, we use the information, or it could be hidden states if we would have more than one neuron. Then the current state, which is provided by the feature variable, and we again will use some parameter values. And this, whatever we're doing here, because we will do something here which is very similar to forward neural networks, but whatever we'll do here, which is basically typically affine transformations, then can again be transformed by a activation function of your choice, and this generates the hidden state at time step t. So could look like this. So we could use, for instance, some weights and multiply them with the hidden state or hidden states of the previous time step. So this would be, depending on how many neurons we wanted to generate, but assume for a single neuron this would generate a single value. Then we would use different weightings here, so different parameters to process the information of the feature variable. So take a look at this here. In the index, we have here weightings which define in which way we use the previous information given by the previous hidden state. And here we have weightings which define how we process the information which is currently provided at time step t. And then again, we have some, like these bias parameters. So it's just parameter values. So in the easiest case, if we have one hidden neuron and if we have one feature variable, we have a single weight multiplied with the previous hidden state. We have a single weight multiplied with the current feature information. And then this adds up to a single value, and we add another single value which is given by the bias. So we have one single value here, and then we transform this value by an activation function. Okay, and then so as I say, all we're talking here can be done multiple times. So that is why it's written here already in this general notation with vectors. So we can use if we use different weights here, then we can generate different values for the hidden states. So we can, generate different recurrent neurons. But what are we going to do with these neurons in order to really generate or to talk about a network? Okay, so if you take a look here, the easiest or the simplest way would, typically we want to process through time until we are at time step t. But in my example, we want to predict something which is at time step t plus 1. So we, in the simplest case, we directly could use this hidden state as our prediction for the time step t plus 1. If we do this, this would be indicated like this here. But now it gets interesting. Of course, we can use these final hidden states. I'm saying final because those are then only the values at the end of the time sequence, and do the same thing with them as we did, for instance, for forward neural networks. So we can use these only the last hidden states here, and then again use some weightings, some different weights then for the recurrent network, in order to put a fully connected layer on top, so like we are used to it from forward neural networks. Okay, so I will show you later in another example, but this is what typically is done, even though in the easiest case. So you would use another weight matrix here, which only takes the information of the neurons at the last time step, and then do the same thing here as we're used to it already from the forward neural networks. So at this point, we add simply a fully connected layer on top of the recurrent structure in order then to generate an output. Okay, and as I said, networks, or recurrent networks, are in general, forward neural networks are very flexible, so you can combine them in very creative ways. And nothing is fixed here. So in my example, we generated a single prediction, but that doesn't need to be the case. Okay, so we can have, for instance, stuff like this here. So we could use the hidden neuron at each time step, if we process it through many time steps, in order to generate what's called a sequence to sequence. This is something that we may use later when we talk about recurrent autoencoders. Don't worry if it doesn't make sense to you right now. But for instance, we could use the information at each time step in order to make a prediction for the time step, like in order, as you can see here, we could use it like this. In order to generate predictions through time at every time step, one step ahead, we simply could use each hidden neuron, each hidden state through the whole process. What we typically use is something like this here. Okay, so typically this is called a sequence to vector because obviously this can be more than one value. But it's, in our case, in my example, it's better. We call it like a sequence to scalar value. But it doesn't matter. So we process something through time and are only interested in the last output. So at time t, because we want to make a prediction for the next time step. Okay, there are even more architectures when it comes to recurrent networks, like a vector to sequence or an encoder decoder. But this is not so important for the things we are going to do here, because we want to apply it more like to a we basically will do it. We mainly will use it for two things: recurrent networks, making predictions if we have something over time, and also processing text information at the end of the course. Here, recurrent networks are also very valuable, and in both cases, we are more interested in these two architectures. Okay. Good. Last information before we go to a simplified example is obviously we can generate deep architectures by not only using a single recurrent layer, so this would be like a single recurrent layer here, we can add another layer on top, and even though it may look complex to you, basically what you do here in the other layer is the same thing as before. However, instead of directly using the feature information at each time step, we use the hidden state information of the previous layer, of the previous recurrent layer. Okay, so but especially if you want to do this on your own, and for instance we're using Keras, this can be defined very easily. Okay, so do not worry about it too much. Just need to know a deep network, I would say, is something that is like this here. So if we really add multiple layers on top, and for instance here we could have a first recurrent layer, then another recurrent layer on top, and then on top we could, for instance, add a fully connected layer. And this is where we're going to start, or where one is going to start to talk about deep networks. But I'm not too focused on the term deep or even not deep network. I'm more interested in the fact that networks, as I said, are really flexible, and we can really define them in the ways we need them, so we can really get creative here. Okay, good. Yeah, just let me take a look if this is going to be too. Okay, this is like the last thing I want to say before we really go to the simplified example. I know this may be shocking to some extent here. Everything else, or at least as far as we're going to discuss it, is not really new. So we do not really need to, even though the architecture is different, when it comes to picking the correct or an appropriate loss function in order to fit the parameters of the value, we do not need to really think new. So if we have like the regression type problem, then we may use the squared deviations or the average squared deviations. And if we have like classifications problems that we want to solve with recurrent networks, then we use, for instance, the cross entropy loss function. And again, here the principles of backpropagation can be applied. As you may imagine, it kind of gets a little bit more complex if you also have to backpropagate through time, but this is something we do not really discuss in any depth here. If you're really interested in, maybe just take a quick look here. I could recommend a book, and let me go here directly in this video, because then I can show you how really you are going to access it. Let me just show you so because there's like the wrong password. I would say there's like one book which really does it very well in being formally correct and still describing these things in a way which are quite good, understandable, even though for people like us who are maybe coming from a different subject or with a different background than, for instance, math or computational science or something. Okay. Okay. Finally, we have it. So sorry if this has taken too long. But the book Deep Learning by Ian Goodfellow, where you have full access here for the text, is where I know is also backpropagation through time is described. So you think you should go through for yourself here. You will find it in the section which discusses recurrent networks. So this is what I would recommend you if you are interested in getting more details here. As we are only applying it and we use the Keras library in order to estimate the recurrent networks, you shouldn't worry about it too much. But I would also, I would like to encourage you to dig deeper, especially if you're interested in. Okay, good. But now to really get a better hold on how a recurrent network works, we will finally take a look at a simplified example. And let's just quickly go there. This is going to be a really easy and simplified example, but I hope this will help in better understanding the architecture of what is called a basic recurrent unit or a basic recurrent neuron. So as I said, the most important characteristic here is that we will have a sequence of values over time. So a single sample that we may take from a data set already is a sequence of some values over time. So let's say that we have here a value of x1, x2, and x3. Okay. Now, as you've seen in the slides, you also start with what is called a hidden state. And this is typically initialized at time step 0. So for simplicity, let's assume that at time step 0, the hidden state has a value of 0. And now, I don't know, let's think about just some simple values here. So assume x at time step 1 equals 1, this equals 2, and this equals 3. Okay. So what the recurrent unit does is at each time step. So in the beginning we have time step 1. It combines the information of the previous of the previous hidden state and multiplies it with a weight, so which is just a parameter value. Here it's a single value because we only have a single hidden state, and we also have, because we only have a single hidden state. So to make sure that this is a different parameter value than the one which processes the information of the featureable, we use the h here. Okay, then we would add the information at the current time step 1 and multiply this with another parameter, which is different than the one that processes the information of the hidden state. So this is indicated by the x here. And then we would add another parameter. This is just as you know it from forward neural networks, in order to have more flexibility. Okay, so as you can see, typically this in the first step obviously is going to be 0, no matter the parameter value, because the initial state is 0. And this is going to be something, so let us assume for the moment, and I hope I'm not making any errors when I calculate it later. Let us assume that this parameter value is set to 1.0. And now also let us assume for the moment that the bias is equal to 0, so that we do not need to take care of it. Okay, so then we would have here 1 times 0.1, which is obviously 0.1. Okay, and now we could further use an activation function here. And to keep it as easy as possible, I use the identity function here, so not really something is done. So identity function just maps the original value, the input value, to the same value as an output value. So, and this is the value of the hidden state at time step 1, which would be 0.1. Now, the thing is, it's going to be, and now we are, we added these two streams of information and we generated the hidden state at time step 1. Okay, so what's done next? Kind of obvious, but let's do it together. So now we use this information, which has in its memory the information of time step 1 at the beginning, and then we could multiply it with some parameter value, and we add new information, which is provided by the value of x at time step 2, and multiplied with the same parameter as before. This is an important characteristic. I'll also come back to that in a minute, because this is what differentiates recurrent networks from a fully connected layer, or or a recurrent unit from a typically fully connected unit as we know it from fully neural networks or forward neural networks. That we are using the same parameter values when we process the information at different time steps here. So again, this is as before, this is 0.1. Okay, and yeah, we would add the bias value, which we can skip here because it is 0. And then we would activate this here, and this is what would deliver us the value of the hidden state at time step 2. Okay, so this is 2, so let's try to do it together. Here at this time step we would have, let's say this is equal to 1 to make it easy for me. Then now we have 0.1 times 1 and plus 2 times 0.1. So we would have, I hope I'm not doing any mistake here, 0.1 plus 0.2, which is equal to 0.3. Okay, so 0.3. And now to go further and process this information through time, let's go here to the state of the recurrent unit at time step 3. And yeah, I hope you're starting to get bored here. So we use the information of the hidden unit at time step 2, multiply it with the same parameter as before when it comes to processing the information of hidden units. Now we use the new and fresh information at time step 3. And we will skip again the bias value, so let's do it together. Here we have 0.3 times, okay, sorry, messing up the colors already. 0.3 times 1 plus, and now we have 3 times 0.1. So I hope this is correct again, and we have here a value of 0.6. Okay, so as you can see, but this is not really the important part, just realizing this on my own. As we have the information here that values increase over time, we have 1, 2, 3. You can see that this is noticed by the hidden state, which also increases its values from 0.1 to 0.6. Okay, but this is, I think important for your recurrent neural networks, that you really understand it aims to process the information over time. So if you take a look at the hidden state at time step 3, it gets new information, but it also holds in its memory what has happened before at time step 2 and at time step 1. Okay, so and as I said, it could be possible, or you could do that. This simply depends on you, but I think you're likely not to have that much of success. You could already use this value in order to make a prediction for the variable of interest at time step 4. But what you also could do is, for instance, you could generate another new model. I'll write this down in red here. So with this last hidden state, you could use H3 times, and now with another fresh parameter without an index and another bias value. So we could also indicate this by 2 here. So that's the second layer. In order again to and use another hidden activation function in order to make your prediction at time step 4 here. Okay, so this is what we were talking about before when I'm saying that you're adding a fully connected layer on top, because this operation here doesn't really make any usage of the temporal process here, and it acts in the way that you're used to from a single layer of a fully forward neural network. So that's like what I call a fully connected layer. Okay, so this is how it works. As I said, I hope I'm not doing any mistakes when I'm calculating something here in my head. This is kind of difficult, or I'm realizing this is difficult for me to explaining it and calculating even the easiest things in my head. And I hope that this makes clear to you what is done when you're using a recurrent unit. And just to really make it clear, how would it look like if you would do the same thing or like a similar thing with a fully connected network or a forward neural network? Then it would look like this. It would have information. It would still have the information at time step 1, 2, and 3, but we would use here you would multiply this with different parameters and add the bias value, and this would then be, for instance, our prediction for time step 4. So this is the important part here. This is really important, like that if we use a fully connected layer or like a forward neural network, then we could still, of course, include the information at different time steps, but this time step here doesn't have any idea what has been provided regarding the information here, because this is separately processed by the different parameter values here. And as we are using above here, always, okay, now I'm running out of colors, as we use always here the same parameter values when we process the information at each time step. This is where the recurrent unit gets the opportunity in realizing that something is happening over time. If you use a fully connected layer, then this opportunity has not been given, because the information at each time steps is processed differently with different parameter values. Okay, so this is a really big step for you to make it in your mind, I would say. But this is what I would say is most important when understanding recurrent neural networks. As you will see in the next video, this is a really simple architecture of a recurrent unit, and there are really fancy ones. But when it comes to understanding the basic idea of a recurrent network and exactly how it differs from a fully connected layer, then I think this is the most important part. Okay, so for the moment, I hope this helps, and in the next video, we quickly discuss one of a fancy, what's called fancy architecture of a recurrent unit. There are others, and I think it makes sense that you partly study them on your own if you need them, and especially if you want to use them, because it's quite easy to use them in Keras. But for the moment, yeah, let's end this video here, and as always, I'm looking forward to the next video, and see you soon. Bye bye.